All right, everyone, let's come back together. So in this next session, we're going to talk about quantum use cases. And in particular, we're going to build out the framework that we started to talk about earlier this morning and talk specifically about the case of quantum chemistry, which we brought up specifically. And your guides for this particular part of the day will be myself and Jayson Lynch, a research scientist in my lab. And we are part of the MIT FutureTech lab. We're one of MIT's largest labs. We're about half economists and business folks and half computer scientists and engineers. And I'm also a group head within the IDE. Okay, so as I mentioned, we're going to talk this through in the framework that I mentioned earlier, which we call the tortoise and the hare framework. And Segung Choi, who is over on the side, was one of our co-authors on this as well. And we published this in a number of places now. Okay, so before I get into the details here, I want to sort of get a little bit of a why this matters part of this, right? What is the actual value of quantum computing to firms? You might say this is kind of a hard question to get at. But I think you actually can do a reasonable job by saying, well, if we think about firms are using particular algorithms, right? And we said earlier that that's really going to matter. Like if you're not using the right algorithm, quantum can't help you, right? Because quantum is only better than classical computer in some algorithms, not all algorithms. And so if you can map firms to the classical algorithms they're using, then you can say, okay, well, is there a quantum algorithm, or might we expect a quantum algorithm to come along where a firm can say, I'm going to switch from using this classical algorithm to using this quantum algorithm. Okay, so what I'm going to show you today is a first sense of, well, what would that look like? All right, and so this is going to be very preliminary. We're only going to cover here 24 quantum algorithms, which is sort of an ongoing process that we're doing to build this up. And then what we're going to do is we're going to say, okay, well, within particular firms' usage, you can look for public indications of the kind of algorithms they're using. And so this is one example of this. This is a patent, right? In this case by Uber. And you see on the circled side here, they say, oh, we're using Dijkstra's algorithm, right? So you can say, okay, now I can go look and see if there's a quantum algorithm that is better for that particular problem. And of course, you can gather this for many, many algorithms and start to get a picture of, well, what are different firms doing with their algorithms, and therefore, where might quantum have an effect? Okay, so we already talked about this. I just want to sort of remind us, right, that there is this sort of equivalence that you can either get a benefit from hardware or you can get a benefit from your algorithms, right? And so in the chart I'm about to show you, what I'm going to do is I'm going to express the advantage that you're going to get from a better algorithm, which is the quantum algorithm, as a fraction of the hardware that a firm is using, because these have these equivalences. Okay, so what does this actually look like if you take a firm like Microsoft? Okay, so to do this analysis, we're going to have to make an assumption. You'll see in a little bit why this is going to matter, but we have to think about a particular problem size that they might be solving for. And as I mentioned, we're going to translate this benefit into the increase in IT capital. Okay, so what is this graph showing? So this graph is showing that if magically quantum computers were suddenly better today, like better than classical ones, and we heard this morning they're not yet there, right? But if they were magically there right now, what would that mean for Microsoft in terms of the actual things that they're doing, at least as far as we can glean it from the public records and things like patents? And the answer is that it would be about a jump in about 3 to 3.5% of their capital, of all of their computing capital, would be like a one-time gain. So if you think about all the data centers they have, all of those things, it would be like the quantum computer would give them that kind of an advantage in what they're doing. Another way of saying that is like being able to use a quantum computer would save them that amount of money in terms of what they're able to do. 3.5% of all of the computing capital that Microsoft has is a big number, right? So this would be worth a lot to them. But you should be a little skeptical here, right? Because I just told you earlier that this is just the algorithmic benefit, and we know that there's this overhead you have to pay because these computers are not as fast. And so you can't get these right away. And that's the rest of the talk is really going to be about exploring, well, why is that true? Like what needs to be true for Microsoft to start getting these kind of benefits? Okay, and I just said that. Okay, so let's talk about the framework a little bit. So the first thing I want to do is I want to generalize a concept that you've probably heard a lot about quantum advantage, which is that quantum computers exist that can outperform any classical computer for some problem, right? This is clearly an important benchmark in terms of saying like, we have unlocked some new capabilities. But I think in terms of the practical part of what most businesses are doing, you're not thinking about like, well, here's something that I have never done before, right? The thing you care about is like, for the stuff I'm doing today, can a quantum computer do it better, right? There are a whole bunch of processes I want to do. And so we're going to introduce this idea of quantum economic advantage. And Carl mentioned this earlier in the talk. We've been collaborating with him for a number of years now on this. And here by quantum economic advantage, we mean quantum computers exist that can outperform any comparably expensive classical computer for the same problem, right? Because this is really what you care about, right? I'm either renting machines or I'm buying machines. Would I rather buy a quantum computer and use that to do the stuff I'm doing? Or would I rather have the classical computer to do this? And this is going to sort of open up our sense of, well, when does quantum actually have an advantage? Okay, so it's going to turn out that there are two things that are really important when we think of quantum economic advantage. And the first one is feasibility, and the second one is algorithmic advantage. So feasibility is just, can this actually be run on a quantum computer at all? Do we have quantum computers capable of running this problem? And algorithmic advantage is that idea of, well, if these systems are much slower, is there enough of an algorithmic advantage to actually kick in? So let's talk these through. So feasibility, right? Quantum computers actually just have to be big enough to solve the problem, right? So if you think about, as you get bigger and bigger problems, you're going to need more and more qubits, right? And if on the x-axis here, we're looking at the qubits are available over time. That's going up, as we heard this morning. And so that means that there's sort of this line where anything below it is solvable on a quantum computer, and the stuff above it is not yet, right? Okay. Now, how do we actually think about this in terms of actual roadmap? Well, here is an example from the IBM roadmap that we heard about earlier. So this is their quantum superconducting systems. And you can see here that on the blue dots, what we've done is put in the actual roadmap that they've announced. And then the red here are extrapolations, right? And that was one of the questions that Olivier brought up earlier is like, oh, well, if you try to project out to 2032, well, how do you know how many qubits that IBM is going to have until they announce it? And so you have to sort of extrapolate. And as we'll show you, you can sort of make different extrapolations, and that is going to give you different answers. But here what we've done is said, okay, well, typically what we've seen is this exponential growth from them, and so we can project that out over time. Okay, now an important caveat here, this is all physical qubits, right? This is the actual, what the hardware is doing. And as we heard about a lot this morning, error correction is a real issue. So if you think about, I'm trying to solve some problem, and I might say, well, I know that I need 3 logical qubits to solve this problem, right? Or 10, or whatever that number is. Say, okay, but once I do error correction, once I make sure that I'm actually doing this on high fidelity qubits, now I have to bring a whole bunch of other qubits along. And that's going to turn out to be actually a very expensive thing. It's going to be really important here. I'm also not going to talk much more about this today, but it is also the case that to do that error correction, you have to do a whole bunch more operations as well. And so that's going to take longer for the system to run it as well. Okay, so all of that is going to mean that if we have this roadmap, we're going to want to translate it from physical qubits into logical qubits, right? And so for one of the calculations we've done, this is about 264 to 1. And so you can sort of start to say, that's when we get 1 logical qubit. What can a 1 logical qubit system do in terms of the kind of problems that we can solve? All right, so feasibility, again, it's this problems must be small enough that quantum computers can actually solve them. Okay, so that small enough is important, right? That's a cap. Let's go from the other side, algorithmic advantage. Okay, so we already talked about this idea of the quantum quantum tortoise and the classical hare. I think a nice way to think about this is, right, if you think about just operations per unit time, our quantum computers are very slow, the classical ones are very fast. But as we gave this example earlier with the Panama Canal, if we think about the actual algorithms involved, right, a quantum system might have a much more direct path that goes to the answer, whereas the classical system might have to go on many more detours to do this. And of course, the balance of those two things is what gives us algorithmic advantage. Okay, so we have the algorithms and we have the hardware. Here, I'm not going to talk in detail about this, but it's important to say there are just a huge number of little technical things that you have to account for to make sure that you're doing this comparison between the relative speeds of them right. And so I've already said quantum computers the hardware is actually considerably slower than classical computers. It's also more expensive on a sort of operation per operation basis. Requires this error correction. Both actually technically require the error correction, but it's a lot more expensive on the quantum side. Also, an important thing here is that many quantum algorithms assume that you have this ability to talk from any qubit to any other qubit. That practical systems are not like that. And so you actually have to have often this connectivity penalty that says, well, maybe I have to communicate from this qubit to that qubit and then that qubit to another qubit in order to do it. You're going to have to take that into account. They also have very different hardware roadmaps, okay? And then the algorithms themselves can have different running times and different mappings between problem sizes and qubits. Okay, so I put this up here not because I expect you to understand all of what I just said here, right? But this is to highlight there are a bunch of these things going on. We're actually going to talk in a little bit about a tool that helps you think about all of these things without actually needing to know those details, which is part of the point of doing this. Okay, so this is going to have an important implication, so let's now talk about what this algorithmic advantage actually looks like. So I want us to imagine that we have two particular algorithms, one algorithm, algorithm 1 and algorithm 2, and they're going to have these different running times. And so people may not have seen this kind of notation before. This is a very common notation for algorithm theorists, but this kind of n notation, or is often written big O of n kind of notation. So what does this mean? Well, you can imagine that when you solve a problem, if you have a bigger problem, it typically takes longer to solve that problem, right? And so you might say, okay, well, if I'm trying to calculate a route between a number of cities, if I'm calculating the best route between 4 cities, that might take a lot fewer calculations than if I'm trying to calculate a route between 10 cities. And so algorithmic theorists write things in terms of this n, where they say, okay, well, if the number of cities, right, was like n, okay, well, I express my running time in some fraction of how that grows over time. And so in this particular case, we're saying this algorithm takes more steps exactly as the problem size grows. So if you go from a size 10 problem to a size 20 problem, you're going to exactly double the amount of computations that you need to do. Okay. Algorithm 2 here, we're saying, okay, well, it's actually going to grow like the square root of n, so much smaller. That's very nice. But there's going to be this factor up in front of it, of 1 million. Okay. So if you haven't seen this notation before, the technical folks who are sort of designing the algorithms in your firms will have seen this kind of notation before, right? And you can ask them sort of what that is. The crucial thing here that I want you to highlight in this is that this algorithm scales better as n gets bigger than this one, right? Because the number of operations you need to do scales as the root of n. But this has this big penalty that you have to pay up front of a bunch of extra work that you have to do. And so what that means is, if you actually think about the number of steps that are needed and the problem size that's involved, this algorithm 2 initially is much worse, but as the problem size gets bigger, it curves around because of this square root of n, whereas algorithm 1 is initially better and then continues on. Okay, so that means that interestingly, there's this threshold point where all of a sudden you switch from one algorithm to the other algorithm. Okay, so this is, and that gives us this sort of this thing of, okay, the left algorithm 1 is better and algorithm 2 is better. So I'm not, telling you this just randomly for algorithms, right? I'm telling you because, of course, this maps to what we're thinking about with quantum algorithms here. And so we can relabel our algorithms, right, as now a classical algorithm and a quantum algorithm. And, let's see if there we go. And so now we get to this situation where we can see, okay, well, if there's a classical speed advantage, if classical computers are faster, right, then you're going to have this penalty on the quantum algorithms, and that's going to produce this kind of a path. So what this is telling us, right, is that for quantum computers, there's going to be some problem size, which is the first problem size where a quantum computer is going to be better than a classical computer for solving that problem. right? Below that, it's just like, the quantum computer is just getting started and the classical computer has already finished the problem, right? That's the challenge here. Okay. So this then is actually our second constraint, right? We said before the quantum computer has to be big enough to solve the problem. We also know that the problem has to be big enough that the algorithmic advantage that the quantum computer has can kick in. And so now we have this sort of opposite sloped line, right? Bigger problems are more attractive, right? And here I've drawn this as a downward sloping line because we're assuming that there's going to be, quantum computers are going to get faster, they're going to get cheaper, there's going to be better error correction. And all of that is going to mean that like that penalty that you pay, that 1 million that was on that previous slide, is going to go down over time. Okay, so the nice thing is that this now tells us, well, problems have to be big enough, and in order to get the algorithmic advantage, they have to be small enough to fit on the hardware. Well, we can put those together, right? Those two constraints, when they're both true, quantum is going to be better for solving the problem. And that's what this wedge represents, right? And so this is kind of interesting, right? This tells us that there's going to be some point in time, right, which is the first moment that quantum computers are going to become useful for a problem, right? We call this the moment of first quantum economic advantage. From that point, and it's going to be at a particular point in time, and it's going to be for a particular problem size. That's really, really important here, right? Because you might say, well, that's like fantastic. Like if 2032 is when I'm going to first get an improvement from quantum, that's great. But if the problem size you need to solve for it is 1 trillion, right? Or the problem that you need is like 10, right? That might not help you if the problem you really care about is 1,000 or 10,000 or something like that. But you can see that you can then draw these lines out here, which is going to capture, well, anything in this wedge is going to be something that has that advantage. And so over time, you could say, well, if the problem I care about is over here, well, that's going to be the first moment that it actually matters for me. And then if you're on this line, this is basically defined by how fast these quantum computers get more qubits. And if you're on this line, it's about how much cheaper they're getting to actually run. Okay. All right, so this is, as I say, the quantum economic advantage framework, this idea of we can actually map out when these systems are going to have advantage. So let me now just sort of summarize in terms of the implications. So first thing, classical is faster, so quantum can only be better when it has a better algorithm. Even then, problems will need to be sufficiently large, right? We wrote this as n star, but they need to be sufficiently large for quantum to provide enough of an algorithmic advantage for it actually to be advantageous. And the nice thing is you can actually check quantum roadmaps from the hardware producers to see when there'll be sufficient qubits to actually calculate this. And this is the first moment that these computers will have quantum economic advantage. Okay, so let me turn it over to Jayson, who will talk you through some of our examples.
Great. Thank you, Neil. And now I'm going to go over some of the examples of studies that we have done using this quantum tool. So here's one that I think people care a whole bunch about, Shor's algorithm for factoring numbers. So over here, we can see there's classical runtime that's exponential, quantum runtime, roughly quadratic. And in this chart, the y-axis is roughly normalized classical time steps it takes to solve this. Bottom, problem size, both of these on logarithmic scales. Right, and so time it takes to run the classical algorithm goes up exponentially, goes up very quickly. The number of quadratic steps has this big jump because of this constant factor overhead, the slowdown. And we can chart when those cross. And so with the inputs here, we see quantum gets faster around 200, problem size of 200, so 200 bits. If you factor in additional costs, we see faster and cheaper, more like 300 or so bits. All right, so what does that mean in terms of when we're going to see this happen? So if you extrapolate out based off of some predictions of how many qubits we might have, this is qubit doubling time of every year, so faster than Moore's law, but not entirely unreasonable. Then we'll see this quantum economic advantage show up for, again, around 200 qubits, around 2032. It's actually quite early. Now, the thing that we all care about isn't necessarily factoring 100-bit RSA, right? Really, what we care about is probably something more like 1,000, 2,000, 4,000 bit RSA. So with this tool, although you can draw a line over at whatever problem size you care about and look at that, and this pushes it out closer to 2035. Based again on these inputs about the assumptions of the algorithms we have and about some predictions on quantum hardware. All right, so now I'm going to walk you through some of what this online tool looks like, hopefully give you a sense of what the inputs are and how you can use it. If you want, feel free to go to the website and follow along yourselves. We wanted to live demo, but unfortunately, I'm going to have to talk you through a few slides here. But also, during the lunch break, Hans and I and other people will be over there facilitating if anyone has your particular use cases you want to look at or just want to discuss with us, get a personal tour of how this works. Great, so the main thing that we'll see is these charts that you've seen multiple times in a couple of different forms, which is how do we calculate this critical problem size number, and how do we calculate this year of first advantage. So to get those, we do have quite a few inputs going into it. So the tool will let you choose what are the algorithms, both the classical and the quantum. And we have some information about known algorithms in the tool already, but you can put in whatever you want based off of your own knowledge, or even counterfactually. If you think there's going to be advances in one or the other, you can plug in those functional forms and look at what that impact would be. As Neil mentioned, we have the connectivity penalty if you don't have all qubits. We have this roadmap where you're able to enter your own data and then extrapolate either exponentially or linearly based off of those points. The how many qubits are needed to solve a problem of a given size, so your effective space complexity of your quantum algorithm. And then the critical factors for your hardware. So how much faster is the classical versus the quantum computer? How much more expensive are we assuming it's going to be per operation? And what's the physical to logical qubit ratio? So the overhead for error correction. Now for each of these, we also have these advanced option buttons. So you can enter in even more detailed information if you want. You can investigate parallel algorithms. You can change how we're extrapolating. And you can have this help you calculate what this overall overhead should be based off of your relative gate speeds of your classical and quantum computer, your error correction overhead, your algorithmic overhead. So we have more details that you can dig into if you want, but you can work at, to some extent, whatever level of abstraction is most useful. All right, and then again, that brings us back to the answers. And you can also add in multiple models with multiple different inputs so that you can compare these graphs directly side by side. All right, from that, I'm going to talk a little more detail about some of the work we've been doing on quantum chemistry, trying to understand how we think quantum chemistry is going to be impacted by quantum computers and when. We're also interested in quantum's impact on machine learning and some other topics. We'll be happy to discuss those with you later. So this is some preliminary work on quantum chemistry. All right, so for quantum chemistry, obviously, the goal is we want to simulate chemistry. We want to simulate the quantum physics that are occurring in here. This was one of the first proposed use cases of quantum computing, really kind of the killer app since its inception. Right, and quantum chemistry simulation is important in a huge number of areas, right? As we heard earlier, pharmaceutical design, getting new drugs, getting new materials for building cars and planes, getting new materials for getting better photovoltaics, batteries, all sorts of huge implications from improving our ability to understand what chemical reactions are going to occur and what material properties we're going to have. Further, faster simulation techniques can allow us to better search for these materials when we're designing new ones, and more accurate methods could allow us to better predict and understand properties and understand why some of these materials work in the way they do. Okay, so a very oversimplified view of the landscape of classic algorithms for computational chemistry. There is a huge plethora of different ways to model this and different simplifying assumptions that are made to make these computations tractable. And very roughly, over a whole bunch of different methods, we have different running times on this x-axis. So near linear to quadratic time algorithms, all the way up to ones scaling exponentially. These all have different degrees of accuracy in different regimes of chemistry, but roughly the ones that are in use, the longer the running time, the more accurate of a prediction you're going to use. Right? And so the ideal case is, we ideally want the most accurate answer all of the time, but it turns out that's computationally way too costly. We can't do that for more than the smallest of simulations. And if you're wanting to run, thousands or millions of them to search for new drugs, you're going to need it a lot faster than that. All right, so here we're going to zoom in on one specific case. Turns out there's multiple different quantum algorithms for computational chemistry also. We're going to look at a quantum phase estimation algorithm. We're going to assume it's approximately as accurate as full configuration interaction, so extremely accurate. And we're going to assume in this particular case that it runs in n-cubed time. As I said, there's some amount of debate over whether those are reasonable simplifying assumptions, and we do look over a broader range in the current paper in progress that we're working on. But for looking at them in these slides at the moment, that's what we're going to take. So again, this would be wonderful, right? If we could have high accuracy, lower computational costs than most of these, but we also have to account for these quantum computers running more slowly. So algorithmic advantage isn't the only thing that needs to be considered. All right, when we do that, here's a chart very similar to what we've had before, slightly more complicated. We have problem size. This is in number of orbitals. We have years on the x-axis. This green line here is the feasibility line that we'd seen before. It becomes dotted, I'll explain in a moment. So that's just number of qubits needed to run this n-cubed quantum phase estimation algorithm. And we have this orange line for full CI, running time. And so there we see this crossing over in 2028. And we also, in the study, say, we don't want to wait forever. Eventually, if it takes too long, we'll just run the physical experiment ourselves. Right? We don't want to wait months for our simulation to conclude in the vast majority of cases. So here we actually put a limit on the quantum running time that we allow. And this gives us a region, this pink region, where we see this quantum economic advantage of this quantum phase estimation over full CI. So again, lots of simplifying assumptions here. These answers change pretty substantially when you change the roadmaps, when you change the slowdown or other inputs. But this gives you an example of how can we try to analyze and understand the landscape of when these might happen. And also, when we do different ensembles of these, can we become more or less confident in some of these predictions? All right, now we can also look over multiple points of comparison. So remember, there were many different classical algorithms. I just gave you the one for the full CI line, which is this orange one. We can also look at a couple cluster with perturbative triplets, so this red line, and other different methods here. And we see different crossing points depending on how much advantage you had, right? So overcoming exponential time algorithm, much easier than these polynomial time algorithms. And if you go further, some of the ones that aren't listed, right, like DFT or Hartree-Fock, not only are we, So not only are we not seeing these converge before 2050, but some of these others are literally off the charts, and we didn't even address. So now we have an understanding that for computational chemistry, it isn't just a single problem, a single technique. There's actually a lot of different things that people want to do at different degrees of accuracy that are relevant. And so it does seem very plausible that quantum computing is going to have huge impacts on computational chemistry, right? There's problems that are completely intractable on classical computers that we might be able to solve with quantum computers. But it's also unlikely that this is going to impact the entirety of the computational chemistry field, right? We're probably not going to overtake very large simulations, right, when we have to deal with thousands of atoms for protein folding or other topics. And we're also not going to deal with cases where you need extremely rapid, but not necessarily extremely accurate simulations. for kind of this first pass filtering for discovering new drugs or materials. Further, based off of a number of our examples, it seems quite plausible that we'll see some sort of advantage in the early to mid 2030s. And advances in algorithms do have a pretty profound impact on when these occur. So going from exponential time down to quantum algorithms that are into the 12th, into the 5th, in cubed, makes significant differences here. And different inputs in hardware roadmaps can change the prediction significantly. Right? If you double your doubling time of number of qubits, that can radically change the number of years and the methods that we see are reasonably feasible to be overtaken. Further, these problems are also sensitive to hardware slowdown. We don't see that nearly as much in Shor's algorithm because you have exponential speedup writing an exponential curve. Here we have linear dependence between the qubit number and the input problem size. So going factor of 10, factor of 100 slower, especially when you have those time caps, can really cut out here. So, especially when we have these time caps, whoops, it can really kill this area pretty quickly just by going a little bit slower. So interesting to see that the sensitivity for these different problems actually changes when you're looking at different use cases. So overall, the value of quantum computing to businesses could be very high, right? It potentially has huge impact in very important areas like chemistry, like machine learning, like optimization. We have a framework that makes some simplifying assumptions that allows us to predict when these different fields will benefit. We can understand what problems have this algorithmic advantage, what problem sizes are necessary for us to see that, because maybe you don't want to solve things that are on exabyte scales, or maybe you do need to solve things that are sufficiently big that quantum computers will be too slow for the foreseeable future. Further, we need to consider what are the actual economic costs of these quantum computers, what are the real slowdowns, and how do we factor these together. So we don't just want this algorithmic advantage, we want these to be faster and cheaper in practice for these practical uses. We've now put this in an online tool that anyone is welcome to use, also welcome to give us feedback on. You can put in your own assumptions. You can put in your own problems that you care about in your business use cases. We've provided some of the roadmaps we found online for different companies. We've provided some of the problems that we have algorithms for. We hope to continue updating this and adding more, but once again, it's up to you to figure out what inputs you believe, what inputs you think are meaningful. And we've been applying this framework to try to understand some of the areas we think there's going to be large impact, including quantum chemistry and machine learning. All right, with that, I'll hand it back to Neil, and I think we'll open for questions.
Great. Okay, so let me just, before, and please, yes, do start thinking of questions that we'll get to. But I guess I want to end with something that you may have seen. So if you go and you read the academic literature on quantum advantage, or for a particular technique, so you might have a chemistry article that's talking about, oh, well, this is the moment where we expect quantum to be better. You'll find that there's a huge discrepancy between different articles about when they predict that advantage will come. And a big reason for that is that there are all of these details that Jayson just showed you, right? So we pulled up in the tool. I'll just pull that back up here. Oh, I might pull it up very slowly. So if you go back one here. So if you think about these things, well, you say, okay, well, how much advantage does classical hardware have, and how much is that changing year to year? Right? If you assume it's not changing at all, you get a pretty different answer. Right? If quantum computers are not getting faster over time, if you pick a different algorithmic form, if you have a different physical to logical qubit ratio like error correction, right? All of these things are important decisions that need to be made when you do your simulation. And so part of the challenge is that many, many papers, when they write about these things, they say, well, we're going to pick a number for here, a number from here, a number from here, and then they do all their simulations based on that. And the problem is, well, if another paper makes different assumptions about those things, now it's pretty hard to compare them. And so what this tool allows you to do is to do those kind of comparisons. You can say, well, I think this is what's going to happen with error correction, or you can take what we have in here as a default. But it allows you to do it on an apples-to-apples basis, comparing the two of them across it. So hopefully that allows you to do it. The other thing I just wanted to highlight here is, if you see at the top here, we have these sort of problem drop-down. So as Jayson was saying, a bunch of problems we have in here. We're just showing you, in this particular case, integer factoring. But actually, there are a bunch that are set in there and a bunch of different roadmaps. Okay, and so one of the things you heard today is that different systems are going the number of qubits that they have differently. They have different error corrections and different fidelities, right? All of those things you can build in here so that you can do those comparisons directly. And then lastly, this idea that was already mentioned by Jayson about that you can put in counterfactuals here. So I think this is really important because these two formulas are very complicated, right? We don't expect you to sort of know that off the top of your head, but you can go look them up for particular things. But what's really nice about this is if you say like, boy, AI seems to be really important in my area, right? I think maybe the classical algorithm is going to get a lot better, right, than it is today because of this. You can say, fine, like, type in some reasonable number here for what AI might be able to do, right? And you could just pick a whole bunch of different ones, and you could just look at the effect and say, like, oh, actually, over a huge range, that doesn't matter very much. That's a super informative thing for you, right? Or even a small change there totally ruins my advantage, and suddenly I don't get anything until 2040. That means it's a pretty unstable. You shouldn't be relying on it. And so what we really hope this tool will do for all of you is to, first of all, you can come to the tool and say, okay, I don't really know about quantum very much. Like, let me just play with this tool and see how important error correction is, or how important these different things are, and just to play with it. See, we heard Will Oliver talking this morning about this idea of like, well, how is the algorithmic advantage you have exponential, or is it only quadratic, or something like that? Well, you can just play with it very easily, right? So that's step one is you can start to get a feel for these things. Step two is you can play with different hardware roadmaps, and you can say, oh, look, if I'm in a trapped ion system, like this is where you're going to get quantum advantage first. That looks very different than if you're on a superconducting machine. Given the problems that I care about, maybe this is the type of system that is going to be most relevant for me, right? So that gives you a second thing that you can do. And then you can start to play with it and say, okay, well, if this looks like this is going to be important for my business in the next 2 or 3 years, or the next 5 years, okay, now I want to like bring some of my technical folks together, and we are going to start to dig a little deeper, right? And this tool is designed so that you can do it at a very high level and just say, I want integer factorization on IBM machines, and I'm going to take all of your defaults. Or it allows you to say, like, I don't believe IBM's thing for 5 years from now. I want to change the roadmap. You can edit it, and you can go all the way down to like exactly what the performance of the system is. And so this allows you to sort of increasingly say, does this matter to me at all? Okay, which system seems to be most relevant to me? Let me really dig in and figure out when I think this is going to matter for me. And so hopefully that starts to give you the tools to actually analyze it. And as Jayson said, we're going to have a session right after this where we're going to actually talk about this. And if you want to come and play with the tool and see how it works, we'll actually show you those things. All right, so with that said, let's open it up to questions. And we have our runners, as always, who can help with this. Yeah, over here.
Thanks, very interesting presentation. I'm just wondering if you have also analyzed if there's going to be economic advantage for current generative AI algorithms. The algorithms themselves are very simple, but it's a scale issue. Is there going to be any time where there's going to be economic advantage?
So that is a good question. There's a whole bunch of different places where in machine learning you could conceivably have some sort of algorithmic advantage, right? You can speed up certain sorts of matrix multiplication. You can use it for helping to pre-process data. There's also fundamentally quantum learning algorithms that have different running times. And right now I find it very hard to say whether or not these are going to show up for a couple of couple of reasons. One is like our analyses are very preliminary. The other is there's complicating factors like if I want to speed up my matrix multiplication with HHL, we need to have some understanding of rank or sparsity of these matrices. You can design your machine learning algorithms to try to favor these things, but it's not totally clear by how much. And you're probably going to have to now go between quantum algorithms and classical computing many, many times. And so this brings up a whole bunch of issues of how am I doing my encoding? How fast is my transfer between classical and quantum computers? Do I have QRAM or access to enough memory? And these are things that we aren't yet able to model very well. So some of the things we're seeing is for many of these problems, you don't have these as gigantic algorithmic gains as you did with, say, Shor's algorithm. And so they also need to be on much larger scales. Machine learning conveniently works at very large scales now, but a lot of the numbers we're seeing for like the first algorithmic advantage is significantly bigger than the number of neurons that we're currently seeing in a lot of deep learning models. Also, I'd like to partially direct folks to Hans over there, who is the person who is specializing in looking at these machine learning applications and can probably give you much more detailed answers to where we may or may not see some of that advantage.
And I would just add that point about these problems having to be very large, right, in order to get the algorithmic advantage, right, that second of the things we talked about, because those problems are large, that also pushes out the timeline, right, because these quantum computers have to have many more qubits in order to do it, and so that's going to push out the timeline for when these things matter. And so that, I think it's, that means that we're likely to get that much later than we get other things like improvements in chemistry and stuff like that.
Yeah, if you're only imagining small polynomial improvements, sometimes you're seeing things like into the 20, into the 30 sorts of ranges.
Other questions?
Hello, my name is Sri Lakshmi. I'm with Analog Garage, which is a part of Analog Devices down in Boston. So earlier in the talk, there was a mention about 24 use cases and more. I might be getting the numbers wrong. But if you can speak more to what are the other spaces where quantum economic advantage is emerging. And the second part to my question is, how do I or somebody else who doesn't have expertise in quantum or quantum physics or the likes thereof, how do we develop a muscle to wonder if we can bring about quantum advantage to this particular field that we're working on, and how do you approach that? Thank you. Sure.
So let me start from the second part of your question. So, a really central part of this idea is, which is what I started with, which is if there isn't a quantum algorithm that is better for your problem, like, classical is going to win. You already have your answer. Even if there is a quantum algorithm that exists for it, what we find is that the quantum algorithm has to be a fair bit better, or it just takes a long, long time. You need very big problems, and it takes a long time in order for quantum to win. And so that sort of pushes us in the direction of saying, well, so it really matters what your existing algorithms are, right? And so this is kind of nice. So another project that my lab has built is something called Algorithm Wiki, right? And Jayson has really been leading that effort. So Algorithm Wiki says, let's think about classical algorithms, right? And you can go and look up a bunch of these things that we put up here, right? So we have that sort of complicated formula for what is the running time of this. You may not know all of those things, but there's sort of a very established community of algorithmic theorists who work on those things. And you can just go up on Algorithm Wiki and you can say, I'm going to look up for my particular problem. So you might know that I'm solving a maximum flow problem or a traveling salesperson problem or something like that, right? And you can actually just look it up. And so that already allows you to put in this tool, like, okay, here is the classical runtime for the thing I care about. Now, what we are trying to do is to then build out that tool to say, like, for any particular problem you do, we'll say, well, what is the best known algorithm for this? Right now, the 24 is what we've already populated. That is a very active set of work that people in our lab are doing to populate that more. But even if yours isn't on that list of 24, you can just go to Algorithm Wiki, you can populate the classical one, and then you can say, okay, well, what would be required for the quantum algorithm to affect it the way I want to, right? And so even though that doesn't get you all the way to what you want, right? Of course, you'd like to know, like, is this even possible, right? And we're not there, and I think the community is still developing those things. But it's enough for you to be able to say, for my problem, right? Actually, I would need, you might be able to say, well, I would need a really, really giant improvement in quantum. That seems very unlikely. This probably doesn't matter for me. Or in other cases, like actually even a small quantum benefit might be enough to really transform what I'm doing. And so it can start to give you that sense of it. I don't know, if Jayson, if you want to say anything more about like particular areas where quantum is coming.
Yeah, I mean, some of the large ones we hear talked about are physics simulation, optimization, machine learning, matrix, anything with sparse low rank matrix multiplication. Right, those are the ones that come up a lot. But in terms of getting intuition for what problems are there, I would say, one, you should look up the specific problems you care about, and then otherwise, you really just need to look at what other problems are there with algorithms out there, what seems familiar. Right, there's definitely hundreds of quantum algorithms that have been developed over time, like Quantum Complexity Zoo or various courses or surveys can give you some notion of what's out there, and trying to understand like what are the similarities to these problems, and is my problem very similar to one of them is probably the best way. But in my opinion, it's very hard to get intuition, or really good intuition for like when problems are very accessible by quantum computers or not. Yeah. Probably other experts in this room have a much better sense, but
it's definitely enough of a developing area that I think people are still figuring out what's possible. Yeah. Okay, any last questions?
We talked a little bit this morning about the pace of quantum hardware development. Given that the tortoise and hare framework talks about both the speed of hardware development and quantum algorithm development, I'm curious if there have been parallel new algorithms developed for quantum computers as the hardware has continued to progress.
So let me answer, and you can tell me if I got to your question. So, like, one of the sort of amazing things about quantum computers, and Will Oliver talked about this today, is that as you add more qubits to them, they're able to sort of utilize that larger state space that the computer gets in order to do more things. And so, sort of intrinsically, when quantum algorithm designers are thinking about it, they're thinking about, well, as the number of qubits grows, that allows me to solve a bigger problem in the following kind of ways, right? And so that is incredibly central to what these quantum computers can do. And so when we have that feasibility line showing that what the quantum computers can do, that's all about that kind of mapping, which is I think what you're trying to get at here. And so we really do see that as a very important thing of opening up this possibilities of what these computers can do.
Can I ask one more?
Sure.
You've looked at a lot of algorithms through the building of the calculator. I'm curious if there's one that offers the most potential or that you're most excited for in terms of what comes next and what quantum computing speaks to possibility-wise. A particular use case for quantum computers.
So I'm happy to go first. So certainly for me, I do think that the quantum chemistry still is one of the most exciting areas for me. I think I think what our research is showing is that this idea that sort of all of quantum chemistry is going to be changed immediately is not right? It's going to be this sort of wave that comes where we get at the very low end with smaller numbers of atoms, smaller numbers of orbitals, like we do get that transformation, and that'll happen, in the next 5 or 10 years. But then there's this sort of march that will happen as these quantum computers become more capable, as they start to run faster, where they will do more and more things. So, but I think what's exciting about that is it's really opening up sort of brand new areas where we know that like a lot of our approximation techniques that we use when you get to 100 atoms or 1,000 atoms are wrong in important ways, and we just can't run them any faster. And as our quantum chemistry algorithms get better, we are going to be able to solve those problems in with much higher fidelity. We'll be able to see new phenomenon, and that hopefully will open up really new discoveries about the kind of materials we can have, the kind of drugs we can have. So that to me is very exciting. But as I say, I think it's we keep drawing these wedges, and I think that's right. Like this is not all of a sudden we hit it and now everything in quantum chemistry is changed. It's like this comes along and we get increasingly more capabilities as the time goes on.
Yeah. So I think from a personal perspective, I also agree. I'm really interested in simulating quantum physics on a number of different levels. I think there's incredibly exciting applications there. And I think there's a lot of interesting ways to like work around and do this in terms of mapping things into those problems. I guess playing around with a tool, I've become slightly actually more pessimistic about the quantum chemistry case than I was before. I think I was overly optimistic before then. I think I've become more optimistic about a lot of other use cases I was extremely skeptical about, which is interesting. But
so, for example?
I had assumed that pretty much anything that you weren't getting an exponential speed up on was just going to be like too absurdly big and far in the future. And it turns out that for some of those problems, there's reasonable assumptions that polynomial speedups seem like they actually matter.
Wonderful. Oh, okay. One more. Take
Thank
us home, Carl.
Thank you guys so much. I just wanted, if you guys can talk about, there are other measures for understanding advantage like quantum volume, or there have been benchmarks that have been put out that are published. How does this add to those, compare to those, enhance our understanding of the ecosystem? Can you talk more broadly about that as well?
Yeah, so I guess measuring the performance of a computer and what it can do, even in the classical sense, is quite difficult. Right? Like we care about how much memory you have, how fast different operations are, what fundamental operations you support on computers, right? Like the RISC or ISP standards are pretty standardized. What your memory bandwidth is, right? We build accelerators in different ways. And so especially when you're trying to get all of the performance you can out of the hardware that we're working on now, it's tricky to measure exactly what these can do and figure out what the right way to benchmark things are. We went right with this notion of fully error-corrected logical qubits as our fundamental resource, because that was, to our notion, kind of the easiest to reason about, the easiest to do these calculations with, and one that we feel like reasonably confident is a useful thing to be thinking about. But like looking at things like quantum volume and these others, where you have to think about like how long do I have enough coherence or low enough error rates over enough gates and things like that. Those certainly seem like quite useful in the discussion.
I guess the one thing I would just add to this is like, I think it really depends what you're using the metric for, right? So if you're trying to say like, I want to understand the development of quantum systems and how they're doing it, right? A lot of these other metrics are super useful for understanding those things, right? But I think for a lot of business people, they may not care about that answer, right? What they care about is like, 2032 is the first time I need to worry about this for my kind of problem, right? And like if these two things change, then that number gets moved up. If these two other things change, then that number gets moved way back, right? And that's enough to do sort of what Andy McAfee was talking about this morning of like if you're watching the news, right? What are the things you should pay attention to, right? If we can give you, like forget all the other stuff, if we can just tell you, here's the date when you're likely to start mattering, and here are the things that you need to pay attention to in the news, and you're like, like big breakthrough in quantum error correction. Now, I need to, call up Carl again and say like, how did this change my, the timeline that I have, right? I think those are the things that hopefully this is useful for. And so I think we see this as being more useful for a managerial audience than some of those other measures.
And also like the decision to work in the fully error-corrected regime and not worry about kind of NISC or noisy qubit errors is a design choice and a limitation of our model, right? If you are strongly confident that that's where you're going to see like the important breakthroughs or advances, this tool isn't going to help you calculate when that happens. That is kind of a different regime.
Okay, all right, so for folks who are interested in exploring this, so over lunch, feel free to grab some food or come right over. We'll be at the table over here. Hans, do you want to wave again? So you're welcome to join us. And Jayson, thank you very much. Thank you, everyone.